Heat Transfer, Chapter 3, Lecture 2, Thermal Contact Resistance. So in the last section, we assumed the perfect contact and interface between two layers. Thus, no temperature drop occurred at the interface. This will be the case when the surfaces are perfectly smooth and they produce perfect contact with each point. However, that's really not realistic. Even flat surfaces that appear smooth to the eye turn out to rather be rough when examined under a microscope. In this lecture, we're going to take another look at the thermal contact resistance and see how to handle that case. So the problem occurs when you have two different layers pressed against each other. These peaks, where they actually touch, form good contact, but the valleys here typically are filled with air, and so that there's not good contact between the air. These numerous air gaps of varying sizes act as insulation because of the low thermal conductivity of the air. So the way we're going to handle this is that we're going to define, look at the heat transfer being a sum of heat transfers. It's the heat transfers through the solid contact areas plus the heat transfer of the gap area. So how do we treat this thermal contact resistance? Well, we simply define a thermal contact conductance HC. HC is defined to be Q dot divided by A divided by delta T of the interface. So here, if you have a interface where two layers are coming together, there's going to be a temperature drop across that interface. That is the delta T across the interface. So again, what we've effectively done is replace this interface layer by another resistance value, because we can define the resistance of the contact point as 1 over H of C, similarly to what we've done in the previous slides. So what is the value of this typical H of C value? Well, our book gives a good table for this. So for air, it turns out it's 3640. Helium is 9520, all the way up to glycerin, which is 37,700. So it can be pretty significant. So our textbook also gives us a table that lists the thermal conduct resistance for various metals. You can see here for stainless, aluminum, various copper, depending on whether it's ground or milled. It gives the roughness, the temperature, the pressure, and the H of C values. Table 3.2 also shows some HC values for some dissimilar metal pairs. For example, stainless steel attached to aluminum, aluminum attached to copper, etc. So let's see how to apply this in a practical problem. Here we have two plates of copper of thickness 1 centimeter each, and you can see at the interface there is not good contact. So here we're told that the thermal contact resistance at the interface is 18,000 watts meter squared Kelvin. We want to determine the thickness of a copper plate whose thermal resistance is equal to the thermal resistance of this interface. So basically we're asking the question, hey, at this interface is going to be some loss of conductance. What equivalent layer can we put in there that would offer the same value? So here, first thing we do, we're going to calculate the resistance, contact resistance 1 over HC. Since we're given the value for HC, we can calculate that. And so R is equal to L over K. So L here's the thickness of the layer, and K is the thermal conductivity of copper. So here we can look in appendix table A3. K is 401 watts meter Kelvin for copper. So we can solve this for L. Basically is what we're doing. So L is here, resistance we found up here. So L turns out to be 2.323 centimeters. So we could replace this interface with this equivalent layer. So you can see basically that what this shows you, that in this case, this contact, this loss of temperature due to the contact area not being smooth is pretty significant. It's about twice it's over the 2 centimeters, which is equivalent to the 1 centimeter plus the 1 centimeter of the original plates. So let's take a look at a little bit more complicated example. So here we have 4 identical power transformers with aluminum casings that are attached on one side of a 1 centimeter thick 20 by 20 centimeter square copper plate. So here we have aluminum attached to copper. The K value for the copper plate is given 386 watts meters Kelvin. There's 4 screws that attach the power transformers. Each screw exerts an average pressure of 6 million pascals. The base area of each transistor is 8 centimeters squared. 8 centimeters squared. And each transistor is placed at the center of a 10 centimeter by 10 centimeter quarter section of the plate. So this part here is 10 centimeters by 10 centimeters. And so, 10 centimeters and 10 centimeters, that adds up to the 20 centimeters. So you got four total. The interface roughness is estimated to be about 1.5 micrometers. All transistors are covered by a thick plexiglass plate, which is a poor conductor of heat, and thus all heat generated at the junction of the transistor must be dissipated to the ambient at 20 degrees C to the back surface of the copper plate in the back. So at the here you can see that 70 degrees C here on the power transformers, and then we have this copper plate attached, and we want this thing to dissipate to 20 degrees C. The combined convection radiation heat transfer coefficient at the back surface can be taken to be 25 watt meter squared per Kelvin. The case temperature of the transistor is not to exceed 70 degrees C. Determine the maximum power each transistor can dissipate safely, and the temperature jump at the case plate interface. So one thing he didn't tell us was the HC value, but we can look in table 3.2. He says it's copper and aluminum, and he also gives us the pressure. So the pressure he gives us is important because we need to know which HC value to choose. So in the table, we don't have one exactly for 6 million pascals, but we got one for 5 million pascals, which is pretty close. So we're going to use the 42,000 value. So before proceeding with the problem, I've gathered some information from the previous slide. HC value is given to be 42,000 watts per meter squared Kelvin. The area of the base for the transistor is 8 square centimeters. The plate itself has a K value of 386 watts per meter squared Kelvin, and the area of one of the bases is 10 centimeters by 10 centimeters. H of the outside is stated to be 25 watts per meter squared Kelvin. So based on that information, we can calculate the R value of the interface. We have to be careful here to convert the 8 centimeters squared into meter squared. Similar with the R of the plate, we can calculate that. And so here the area of the plate is 10 centimeters by 10 centimeters. So converted to meters, that's 0.1 times 0.1 or 0.01 square meters. And similarly, we can find the resistance value for convection as 25 watts per meter squared times the area for the base of the plate. So adding all those resistance values up, we get a total resistance value shown here. We can calculate Q dot. It's delta T over R total. Delta T is 70 on one side and 20 on the other side. Divided by R total, 12.4 watts. We can calculate delta T at the interface, which is Q dot times R interface, 0.37 degrees C. So therefore, the power transistor should not be operated at power levels greater than 12.4 watts if the case is not to exceed 70 degrees C.